Yeah. So Shong Yang has some question. Go ahead, ask.
Hi, I have two naive questions for Professor Yang. So in your exactly solvable model for geometry change, why do you only put an isotropy in the form factor, but not in VQ? And another question is that is this model only applicable to CFMC, or it applied for all fractional quantum Hall states and regular crystal states?
Okay, so let me answer maybe the second question first. So as I said, this model this model does not specify a fitting factor. So the statement here, for example, this equation applies to all fitting factors. I applied specifically to 1/2 just to measure with Mansour's experiments. I didn't fully understand your first question. It's just the model itself. So this, of course, has nothing to do with the interaction. So this is the one-body property that comes from the band structure, and the interaction is my choice, and I chose it just to make it exactly soluble. I chose a isotropic Gaussian. Now, if you want, I can choose a anisotropic Gaussian, and the model would still be exactly soluble, except this formula will have to be modified. Does that actually answer your question?
Yeah, but I think I just don't understand why you choose VQ in this way.
Well, because it's Gaussian. I want this Gaussian to be combined with this Gaussian. If I don't have a Gaussian here, then I'll have a complicated function. I wouldn't be able to extract this relation exactly.
Okay, I see. Thank you.
Yeah.
Thank you.
Next question will be coming from Bart. Bart, can you ask your question?
Yes, thank you. So this is for Kuhn.
Okay.
I didn't quite understand at the very end where you were showing, I guess, the relative weights of the m equals 2 and m equals -2. Yeah, and then that was done from some exact calculation of a Pfaffian state, or
okay.
then,
So yeah, I rushed it a little bit. So this is for Coulomb interaction.
yeah.
So this is for exactly Coulomb interaction projected to the second lambda level. This is Coulomb interaction plus a small three-body interaction with positive coefficient. This is Coulomb interaction plus a small negative three-body interaction.
So, but what if you do? This is from an exactly size. So you're doing an exact diagonalization.
Yes.
Is it on a sphere? So
It has to be on the torus.
It's on a torus. Okay, so it's not biased. Okay,
no.
and what happens is in that case, if you don't wind up with a pH Pfaffian, but you wind up with some kind of it's just a symmetric state.
Searched for pH Pfaffian for a long time. We couldn't find a Hamiltonian that would stabilize it.
No, it's okay, but I'm saying you did a calculation with. Okay, so the statement is that if you have no three-body interaction.
Yes, that's this case. Yes.
So then you're getting something which is a linear combination of a Pfaffian and anti-Pfaffian. Is that
exactly?
Okay.
If you have exact particle symmetry, you will have also the symmetry between +2 and -2.
Yeah, that's what okay. But so that is not I was interpreting it as a pH Pfaffian, but it's not a pH.
No, it shouldn't
be something quite different. And then thank you. You've
Okay, the next question will be coming from Jainendra. Can you ask your question, please?
Yeah, so I would like to finish my answer to Duncan's question. So he asked whether this model can be interpreted in terms of a multi-layer model. So at least I don't know how to do it, and I think it may not be possible for the following reason. So unlike lambda levels, unlike layers, lambda levels are not equivalent. So lambda levels have different degeneracies. And I think more importantly, there is an ordering to lambda levels. So if, for example, for an incompressible state, I cannot, when I want to create an excitation, I have to do it from the topmost lambda level topmost occupied lambda level to the lowest unoccupied lambda level. And I think, and let's say if I move away from incompressible states, then I empty the topmost filled lambda level, or I start filling the topmost unoccupied lambda level. So I think the counting of states in our model would be very different from the counting of states in a model that considers multi-layers. And of course, in one limit, we get a Fermi sea, which also I don't think how one would get from a model with multi-layers. I also have a question for Kun.
Hi.
I find it rather impressive that by adding such a small three-body term, you see such a big effect.
Well, that's because the system would spontaneously break particle symmetry if you go to large system size. So it's like
Right.
the Ising model. Infinitesimal field will tilt the spin up or down. It's exactly the same thing here.
So the question is, if you add such a small, let's say either positive or negative three-body term, does the ground state become either Pfaffian or anti-Pfaffian to good approximation?
I believe so. And Duncan and Ed done numerics way back to demonstrate that. Duncan, you would like to comment on that?
Yeah, in principle, both the ground state is both the Pfaffian and the anti-Pfaffian. They're both present in the ground state. The Pfaffian and the anti-Pfaffian are degenerate with each other, with a pure two-body interaction. So if you do it for a small calculation, they mix, and one combination is slightly lower than the other in energy. But when you go to bigger and bigger things, you'll find the ground state is highly degenerate with a mixture of both. Will include both the Pfaffian and the anti-Pfaffian.
I see.
So you get on the sphere or something like, well, sphere won't get on the torus, you get you'll have a fourfold degenerate, you'll get an eightfold degeneracy basically. A little bit of three-body thing will split them. So this is very special to half filling. If you did it at a quarter filling, you wouldn't get this degeneracy, but at half filling, with only two-body interaction, you have you'll have broken particle hole symmetry. If you have the Pfaffian, you'll also get the anti-Pfaffian.
I see.
Okay, so we have Gabor next to ask the question.
I just have a
Gabor.
quick question for Kun.
Gabor.
So it was discussed, and also in your drawing, you showed that sometimes the graviton is in the middle of, the continuum of collective modes.
Right.
And so in your models, did you have any of these or collective modes?
So
Basically, what I'm asking is, why do
Yeah.
you have such a nice resonance? Can you also have, say, in the collective modes, a state that has a spin of -2, whatever, and then, they kind of both would do something together?
So let me try to answer the question this way. Yeah. So our calculation takes into account all of these states, and they are all here.
Okay, that's the background.
Yeah, that's the background, which is almost exactly zero. Well, you see a little bit of that, and you see them here. So the striking thing is that they are extremely sharp, although not infinitely sharp, despite the fact that they are in the continuum. Now, as discussed earlier by other speakers, you can try to cook up models in which this actually detaches from the continuum, in which case they would be infinitely sharp, just like the GMP mode. But these models are not realistic. We want to actually calculate things that would correspond to real experiments. So they shouldn't be infinitely sharp.
Okay, thank you.
Answer your question?
Bo,
thank
can you ask your question? Bo?
Oh, hi. Yeah, hi. I have a question for Professor Yang. Thank you very much for the interesting talk. And I think to continue a little bit on our brief offline discussion, I may have missed your explanation about the graviton mode in the Q = 0 sector. Normally for the magneton rotor mode, my understanding is that the graviton mode is orthogonal to the Q = 0 sector, right?
Exactly. So that's why I would prefer to think explicitly at k equal to 0. So remember, well, just to remind you, this operator has exactly 0 momentum because it's q and minus q.
Right.
So for the V1 pseudo potential, this is actually precise. Well, actually not this version, but this version is precisely the off-diagonal Haldane pseudo potential that you introduced. Your paper was actually extremely important for our understanding. So you can discuss and understand gravitons just by thinking about 0 momentum excitations using actually your off-diagonal pseudo potential.
Right, but
the wavelength limit, yeah.
So low Q and low negative Q only connects Q equals to 0 to Q equals to 0, and all the states there have a 0 angular momentum and 0 momentum.
Exactly, yeah.
Dynamic limit, right? So how does that couple to a spin 2 excitation? Because
well,
you
I mean, carry a spin 2 because it's d plus id. So the angular momentum is here.
Right, but when the summation will give you 0 because low Q, low negative Q will give you something that's rotationally invariant. It depends only on the magnitude of Q, I suppose.
No. As I said, if you put in the V1 pseudo potential, it's exactly your off diagonal Haldane pseudo potential. It's not 0. It will kill the laughing state for the plus case.
Right.
But in general, it's not 0.
Okay, I thought that finite systems it's not 0, but for translation invariant system. I have to think about it. Maybe a related question is that you're having this graviton mode at Q equals to 0. So normally we can think of the magneton-rotor mode as a branch of elementary excitation where all the states are basically composed of multiple rotons and the gravitons, right? So for this particular state at Q equals to 0, can I also understand it as is it composed of this magneton-rotor mode, or is it a new mode?
I mean, in principle, it's possible, but I can't see how it can give rise to such sharp resonances.
I see.
And as I said, the physical picture, which I actually gained by reading your paper, is that all what it does is to turn a m equal to 3 pair to m equal to 1 pair. I don't see how to understand that in terms of a magnetoroton.
So it does connect the section m equals to 3 to m equals to 1.
Yeah.
But that's what I'm missing here is that this matrix element between 0 to n, the ground state to an excited state at n, the structure factor in some sense of that matrix element should be only dependent on Q, the magnitude of Q. So when you sum over.
No.
Okay, maybe I'm missing something.
Okay, so we might be actually mixing things up because this Q is like a relative momentum.
Yeah, I know.
Yeah. So the total momentum is fixed to be 0 actually.
Okay. I'll think about it. I think I'm missing something. Thanks.
We have one more question for Kun, I think. It's from Mansoor. Mansoor, can you please ask your question?
Yes, thank you. Nice talks, both of you. Actually, my question is for Jainendra.
I see. Okay.
So I have 2. Is that okay, or do you want to finish questions?
No. We have time. So go on, ask.
Yeah. So Jainendra, two questions. One is, are there any experimental verifications that one could make based on what you presented? It seems to me if it doesn't include Landau level mixing, it may be hard to make quantitative measurements and compare. That's one question. The other question I have is the nu equal to 1/3, which is the nu equal to 1 of the composite fermions. If you start from 2 flux composite fermions, if you start from 4 flux composite fermions, is nu equal to 1/3 also nu equal to 1 of those composite fermions according to this theory or other theories? That's a general question.
Yeah, let me, so as for your first question, as I mentioned in the talk, this model is not expected to be a realistic account of experiments. So this is a model that we like because it's exactly solvable. It considers a different limit. So it's kind of a new twist on exactly solvable models. But we think that it does capture the topological properties of various fractional Hall states that are observed in experiments.
I see.
So this does not provide a realistic account of lambda level mixing. Okay, it's a theoretical model. For your second question, yes, one can think of, so this is now going back to the previous models, the standard composite fermion theory. You can certainly think of 1/3 as filling factor -1 of composite fermions carrying 4 flux quanta. And in fact, one can construct states and excitations, and this is as good a description as filling factor 1 of composite fermions carrying 2 flux quanta. The question is which one is more natural. So as you know, we can think of filling factor 1 as filling factor -1 of composite fermions carrying 2 flux quanta, but this is not a very natural description because the gap at filling factor 1 is not determined by the interaction energy, but it's by the cyclotron energy.
Right.
So I think
I am sorry, I have to stop you guys because
Okay.
we are finishing our time, but I think
Okay.
it's wonderful to discuss. And thank you, both the speakers. It was wonderful talk. So
so
I
we can-
just clap
we
on
can
behalf of
discuss later.
everybody.
Yeah.
Yes, thank you so much.
Okay, so with that, I think we can get set up for the second session. So our first talk will be by Semyon. So if you want to.
Yeah. So I will share.
Okay, and I guess just as a reminder, the same rules as apply as in the first session.